It's working. Okay. Okay. So welcome everyone. We need to continue with the session. So now I'm glad to introduce Amelia Langley from IMEC. She will introduce the latest results for SOLIDIFY project. So please, Amelia.
Great. Thank you very much, Maria. It's a pleasure to be here. So thank you everyone as well for attending this event. It's really quite exciting to bring the cluster together again. So yes, I'm Amelia Langley. I'm from IMEC, based in Leuven, Belgium. And I am representing project coordinator Philip Verreken, who is the principal investigator for this call. My colleague also, Louis, is in the sea of people, yep. So if you have any questions about IMEC in general and what we do, please feel free to approach us. But today I want to talk about SOLIDIFY project, and this is really all about liquid processed solid-state lithium metal batteries. And SOLIDIFY really comes from using a liquid precursor that then solidifies to bring an all-solid-state battery through. And we use different architectures and processes, which I'll show you, but I don't want to give all the meaty details away. Really, there's topical sessions today and tomorrow, which will go into more depth, of course, around the technical side of SOLIDIFY and all the projects. But hopefully this serves as a nice overview of what we're up to in the project. So, of course, it's not IMEC, we of course coordinate, but we have a consortium of 14 partners spread across Europe. So we really cover the entire battery value chain with these wonderful partners who are also involved in the other projects in the cluster as well. So it's really not just one person or one institute. It's really a nice collaboration. That's what's so lovely about European projects. So we're spread across Europe, of course, European project, and we really go from, at least at IMEC, from the materials side, and then we move all the way through to our end users, including CRF, VDL, and that's in buses and battery-operated vehicles. So then the objectives. So I won't dwell too much on all the writing here, but really what we would like to bring forward in this project now that we're coming to an end, we plan to finish in May 2024, May-June 2024. And we want to bring through manufacturable materials and processes. That's really a core aspect, of course, of this cluster. And we intend to deliver full cell assemblies with 1 amp hour pouch cell prototypes. And in terms of the material research, which perhaps we're more interested in, really depends on the person, we want to give solutions that enable this manufacturing, and then, of course, improvement for cell integration steps as well. As we all understand, there's many challenges involved, which I will go into a little bit later. But this schematic really shows our plan for the project. Now we're coming to the end. We go from TRL3, where we have lab-based studies, coin cell predominantly, of course, moving to TRL6 by the end of the project in 2024. And with that, of course, comes really important aspects on the outlook of the technology. So, of course, we're developing new materials, but what's really important is to ensure there's a full life cycle assessment. Are these actually sustainable from an environment, cost, and social point of view as well? So this is the overall trajectory of the project. So now I will delve in a little deeper into what we're actually using within these SOLIDIFY cells. So here I have a schematic of the intended cell, or the cells we're actually now making. And this is all based on, first of all, a protected lithium anode. No, I can't use a pointer. A protected lithium anode, of course, lithium metal. And then we have what's quite unique to this project is this nano SCE, this nano solid composite electrolyte that's been developed at IMEC and in collaboration with Solvionic. And then we have, so this is a separator, and then we also have the active material at the moment. Well, we actually use NMC 811. And we also include nanocoatings on this active material, so that's another unique aspect of these cells. And then composite cathode, so we actually incorporate this nano SCE into the cathode architecture itself. And we use this so-called solid to liquid approach, where we effectively start with a solid precursor of our nano SCE. And then depending on the liquid precursor that we're using, we can then solidify that entire system. So that's where the name SOLIDIFY really comes from. So delving in further to each constituent component, we've developed high ionic conductivity nano-solid composite electrolytes, so more than 1 millisiemens per centimeter, with peak limiting current, limiting current so far more than 1 milliamp per square centimeter. These are quite important aspects, of course, of the electrolyte, as we all know. And there are two, let's say, veins that have been investigated within the SOLIDIFY project with regards to the electrolyte. There's an inorganic-based nano-solid composite electrolyte, and there's also this heterogeneous doping of a polymerized ionic liquid. And so there's actually this pill system, the latter system, that we've then been focusing on in the last part of the project for multiple reasons. One being that we can obtain much thinner separation compared to using the inorganic counterpart. We've also been able to obtain improved ionic conductivities because of this pill separator. And as you can see, you can actually have something that we can handle relatively easily. I think it depends on the person, but if you saw let's say the preliminary materials, these pill electrolytes can be quite difficult to handle, but with a certain doping we can actually improve the mechanical strength as well of this system and the ionic conductivity as well, as you can see here. And then we can see with doping as well, we've improved the lifetime or the cyclability of this electrolyte as well. There will be more information in a topical session later today on the electrolyte, so I won't go too far today, but please make sure you also attend this topical session. With regards to the composite cathode, the so-called composite cathode, where really what we mean here is we have our NMC electrode already prepared, and then we actually infiltrate this electrode with our liquid nano-SE precursor. So that's where the composite side, let's say, comes in. And there are two core aspects of the cathode, one being the architectures. So within the project, we've looked at 3 different architectures, let's say a single-step process or a typical planar process or architecture. We have this trenched architecture, which has been developed by TU Delft. I've got the references here if you're interested as well, where effectively, say trenched, perhaps a little misleading, we have like pinholes in the cathode itself. And this actually enables, one, for the cathode to be quite flexible. One of the aspects is that we want to use high-loading cathodes, and this pinhole architecture really helps with the flexibility, formability of the cathode. And then secondly, it really also helps improve the infiltration of the electrolyte into the cathode itself. And we are, similar to previous projects just presented, looking at quite high loadings, very high loadings, I'd say up to 10 to 12 milliamp hour per square centimeter. There are challenges, of course, that have already been highlighted with using high loadings, but that's the intention and what we're working on right now. And in collaboration with a partner, Powell, they produce nano coatings on the active material, the particles themselves, before the cathode is assembled. And this predominantly is for improved lifetime and cyclability of the cells. And then finally, let's say the protected lithium anode. So there's 2 aspects again here, one being the protection itself, typically a lithium nitride protection, quite a simple process that we've been able to incorporate into a roll-to-roll process for developing this coating. And we're also looking at laminating with pill as well. That's another aspect that we'd like to look at. But really, we're using a thin lithium on copper foil for this, less than 30 micrometers in thickness. And then we also have some 3D structures coming through. So I don't have really results on the 3D structures in terms of their cyclability, but the idea is that if we improve sorry, words are evading me. If we improve the surface area of our anode, we can then actually increase the currents that we can actually put through the process. That's the theory. That's what we're working on right now. So hopefully bringing through 3D structures. And this, for example, is using laser ablation that we've developed at IMEC. And you'll see that with the treatment, with, for example, it could be a lithium nitride treatment. We can improve the lifetime of the anode as well. Finally, it's nice to show where we're actually at with the cells themselves. So this is really ongoing work. It's not the end result, let's say, but we thought it would be nice to show what we could expect from a final prototype. And we have challenges which will be highlighted in later topical sessions. At the moment, our first prototypes for SOLIDIFY, we've been able to obtain more than 450 watt-hours per litre. You'll see here on where we expect to go with the thickness of separation. We're at quite a high separator thickness, but this is very much preliminary. We have issues, of course, challenges with solid electrolytes, like many others here, with their mechanical stability. So with the doping and improving this mechanical strength, we hope to then, of course, decrease that separator thickness, moving into the latter part of the project. So to May 2024, the KPI, of course, for this cluster is 1,200 watt-hours per litre. Very ambitious, I think we can agree. But the intention, of course, is to get there. So just as a snapshot in time of where we are, might be quite helpful. And in terms of upscaling and manufacturability, which is really a core focus of this project, we have made multi-layer pouch cells, not performing, of course, at the 450 watt-hours per litre. When we move from, say, coin cell, small pouch cells to much larger pouch cells, so this, for example, is a 10 by 15 centimetre square pouch cell, we then encounter more issues with effectively the materials struggling to deal with the upscaling. And so some aspects are, of course, already scalable in a roll-to-roll process, like the anodes and the cathodes themselves. But we're finding challenges with the manufacturing of like a roll-to-roll process of the composite cathode to the infiltration step of the cathode. That's very difficult, just with homogeneity of the overall electrolyte layer on top of the cathode. And there'll be more information later. And also the trenched architecture as well that we'd like to bring through. With the high loadings, as you can imagine, we do experience issues with then moving this to a roll-to-roll process. So then with these challenges that we already see, perhaps we can't tackle all of them within the project, we then intend to have a follow-up project as well. Okay, I think I've taken up enough time, but of course there's contributions to all the other topical sessions later today and tomorrow, so please do ensure you attend to find out more. And these are publications that I've mentioned throughout the presentation. And thank you very much for listening. And we have a Q&A after the next talk. Thanks. Thank you.
Thank you. Thank you, Amelia. Okay, so we will move to the last talk related to the project that, let me check. Here, duplicate. Perfect. Okay. So Aras will introduce SUBLIME project. So.
Hello, everybody. My name is Arash, and I'm co-coordinator of the SUBLIME project together with Jens Ewald from FEV company. So SUBLIME is focusing on solid-state batteries with a sulfide-based solid electrolyte. And as you know, sulfide is very challenging to work with a lithium anode, so I show the challenges and the progress that we had towards this direction. So similar to other projects, SUBLIME is also consists of a large consortium, including 14 companies and research institutes. And the aim is to develop a lithium metal battery with a sulfide-based solid electrolyte, high nickel content NMC, and lithium metal anodes. And we are also planning to make pouch cells with capacity of from 1 ampere hour to 10 ampere hour. And at the moment we are producing small pouch cells. So I skipped this one. So I have categorized the process of the work. in three categories. The first step is the material synthesis and testing. The second step is upscaling of the materials and fabrication of the electrodes. And the last step is to make multi-layer pouch cells. So in this project, we are also focusing on two different types of cells. The first one is a high energy cell that has to fulfill 450 watt-hour per kilogram. And the second one is the focus on high power cell that in this case, the most important thing is to reach 5C charge rate. But up to now, most of the activities were focused on developing materials for high energy cells. Sorry. So I go quickly over the different steps that were involved in making the cells. So in the terms of material synthesis and testing, so we have to develop the basically cathode, solid electrolyte, and anode for these cells. So maybe I show it here. Yeah, for the solid electrolyte, basically the solid electrolyte with reasonable conductivity of around 2.5 millisiemens per centimeter was developed for high energy cells, and also a second type of electrolyte with 3 times higher conductivity was developed for power cells, and these are somehow mass produced. It's the first one is produced in kilogram scale, and the second one is in batches of 100 gram, and this is done by Solvay. For the cathode, a special NMC cathode is developed for both passes by Umicore, so with the small particle sizes and special types of coating that allows us to reach to gain high capacities at a high C rates. For example, at 1 C we can get a capacity of 180 to 190 milliampere hour per gram with this special type of coating. With the anode, for the lithium anodes, so we focus on three approaches to make coatings on lithium anodes. So it's polymer coating, ALD, and thermal evaporations. So this is done mainly by TNO-AB and Solvay. And a very recent result we achieved was that to get a stable coating versus sulfide electrolyte and with a very low interfacial resistance, as you can see. And this was achieved by ALD coating of aluminum oxide on lithium anode. So then we put these materials at the test. So we fabricated coin cells with this type of material that was developed, and you can see we can get high capacities at room temperature. So it shows the proof of concept. The cell is working. I have to emphasize that the cell that you can see here is with the normal lithium anode, and this lithium anode was not coated. So therefore, the cell stopped working after several cycles. But this shows that the cathode is working, solid electrolyte is working, and lithium anode is working. But we have to upscale the lithium. We have to mainly focus on the development of the coating for the lithium anode. So next step was to upscale and make electrodes towards making single layer pouch cells. So a lot of activities were done at the AIT towards making freestanding electrolyte layer, and at the later stage, for example, a lot of activities were also done at the Fraunhofer Institute and the Braunschweig Institute to fabricate these cathode electrodes. So you can see a lot of cathode electrolytes have been fabricated with these cathode components, and also bilayer cathode and solid electrolyte layers have been fabricated with upscalable method. On the other side, for the lithium anode, so we further focus on the development of the coatings for lithium anodes, and you can see here, maybe it's a bit small, but then the new coatings that were developed are stable up to current densities of around half a millisiemens, half a half a milliampere per square centimeter. So it is like C over 2 if you have a mass loading of 1 milliampere hour per centimeter. And at the moment, the first generation of the pouch cells have been produced and are being tested. This is just very new, very recent activity. But for the first generation of the cells, this lithium anode was not ready yet, and we used indium anode. So the first generation of the cells are being produced with the indium anode, and now that we have recently achieved these promising results for the lithium anode, the next generation of the cells will be produced with the lithium anode. So regarding the upscaling for multi-layer pouch cells, and to reach the targets, we see that based on the experimental results that we have at the moment, we are using let's say 70% carbon active, 70% cathode active material in the cathode, and with an extremely high, we can make electrodes with extremely high mass loading, but then the thickness of the solid electrolyte is a bit high, 50 micrometers, and by doing a theoretical calculation, this gives us an energy density of 320 watt-hour per kilogram or 460 watt-hour per liter. So if you want to really achieve the end goals, so you see we have to reduce the electrolyte content in the cathode by 10%, very high NMC content of 87%. Mass loading is a bit more acceptable, is 7 milliampere hour per square centimeters, and then we have to really stick to 20 micrometer thickness of the solid electrolyte, and using all of these criteria we can reach the target. So it is very challenging, as you can see here. So the next steps, this will be discussed in the upcoming sessions. P2D and P4D models were developed at the coin cell level to fit the experimental data. This will be discussed in the next sessions. I just quickly present it here. And recycling process also fulfills the requirements of the EU. So around 90% efficiency can be obtained based on this cell chemistry, and there is an entire session discussing these results. So I will also skip this. But one other thing that I wanted to just quickly mention is that basically the cells that we are focusing on in this case for us is all solid state batteries, and we need a lot of a high stacking pressure. So for us it's at least 20 to 40 megapascal, but there are semi-solid state cells that you can use them with a pressure of less than 1 megapascal, and you can see if you just increase the pressure from a bit below 1 megapascal to 2 megapascal, this is the best. I think this is the Samsung cell that with this anode-less cell that operates at 2 megapascal with a very low pressure, and by just applying this pressure at the pack level, our team did some calculation that at the pack level you have to work with a more robust pack design, and you lose energy density by 12%. So this is also something that we have to consider at the end, because this stack pressure, at the moment we don't care, we just want the cells to work, but this is something that has a huge impact by the end user. So at the end, just to summarize, the aim is to make cells with a extremely high energy density, 450 watt-hour per kilogram. As I said, this can be achieved based on very extreme conditions. There are some activities on providing at the second pass. We have the cathode and solid electrolyte ready for this. I'm working on making a lithium anode ready for this pass. And as I said, sulfide electrolyte NMC cathodes are developed and upscaled, and bilayer cathodes are also produced, and the initial pouch cells are fabricated, the main challenge so far is to make a lithium anode to work, and at the moment we are making monolayer pouch cells of 40 milliampere hour, but we are moving in, and hopefully next we are moving towards forming, producing 1 ampere hour multi-layer pouch cells. Yeah, so that was basically some of the results of this project. Yeah, thank you very much.
So we are a bit late, but we will take some time for questions. So if there is any comment in the audience. Yeah. Maybe I would like to ask to the speakers to come here, please.
So do I question the last project or every project?
Up to you.
All right, since we have these slides, for SOLIDIFY I would like to know how do you process electrodes and separators? Is it a solvent-based technique?
For SUBLIME?
Yeah, so SOLIDIFY.
This is,
Oh no, sorry, for the SUBLIME, yes.
Yeah, it's a extrusion-based process and also with coating. So there are different types of coatings that are being applied, and my colleague Arthur, he's sort of talked about it this afternoon.
All right, okay. So extrusion is a dry technique without solvents?
A little bit of
Still a little bit of, okay, thank you. For what about now? Yes, sorry.
Better.
Yeah, so the other project, SOLIDIFY, how do you produce and characterize the coatings on NMC?
Hello. Oh, yep.
Yes.
Yeah, so this is produced by Powell, so they do a lot of the characterization, but the coatings are made by ALD. And then they characterize their suitability or cycle life first with a liquid electrolyte. And then with promising results, they then would characterize its performance with the solid electrolyte that's developed in the project.
Okay, so is it scalable?
Yes, so they use there's a phrase for it, but it's a spatial LD technique where they can pass the particles through, and it can produce at quite high volumes in the up to the ton. At the moment, they're moving up to a ton scale. So
wonderful.
That's at Powell. So yeah, not my expertise, but I know that it certainly is scalable.
How do you know if it's nano? You mentioned nano coating. You only
yes.
characterize by performance, but how do you see
yeah, of course, then there's materials characterization, so looking at the morphology and cross-sections of these particles as well, which, because it's with Umicore technology, we can't show this kind of data, but then they have their own in-house characterization to ensure that they are actually coated.
It's a kind of TEM, right?
Pardon? Yes.
TEM or
Yeah,
XPS,
exactly,
something like that?
Exactly.
Okay, thanks. On your page 7, you showed the performance of solid electrolyte.
Yeah,
was it room temperature or high temperature?
So that particular cell was at 40 degrees. So we're capping at 40. So we have done room temperature cycling as well. But at the moment, with VDL, their performance is from typically 0 to 40 degrees. So then to let's say boost performance, we tend to go at slightly higher temperatures.
So your 1.4 millisiemens per centimeter relates to 40 degrees?
Yes, yeah, exactly. Okay. So they're measured at each temperature, but for this particular cell, yes, at 40 degrees.
Okay, sorry, can I ask more questions for other projects? Okay.
Yes, go for it.
That's going to be fast. Okay, safely move. Why do you need to be more than 40 micrometers? On your slide 3, you showed you need more than 40 micrometers.
Oh, in my slide 3?
Yes.
But are you talking about the electrolyte?
About your anode, 40 micrometers of lithium.
So actually we aim to go, so the first generation we had was for 50 micrometers, but we need to consider that this is for 2 cell units, so this means that we have 25 micrometers for each cell unit. And later we decrease to 40, so it's not that we need to, so we want to go below this value mainly for the energy density, because even with 40, we are talking about 20 micrometers for each cell unit, so we are in an excess.
Okay. So actually you have all your lithium in NMC. You don't need extra lithium if everything works well, right?
In ideal case, with an anode-less technology, yes,
Yes.
this will be the ideal case.
Yes. Okay. All right. I didn't catch right the solid electrolyte target in your case. First you talked about 1 and then you talked about 0.1. On your page 7, it was 0.1.
Are you talking about conductivity?
Yes, the ionic conductivity of your solid electrolyte.
Yes, so maybe it was written, so in one case was written like 10 to minus 4, that at the
Yes.
end is 0.1 millisiemens. So
Yes.
it's the way in which it was written.
So this is the target.
This was the target that we were aiming, but for sure, where you are talking about thick, really thick electrodes, if you want to go to high currents, we will need to go beyond this target. I mean, we need to go to higher ionic conductivity, but not only in the electrolyte, this is also a lot to do with the electrode. So for that reason, Tech has been working a lot on improving the conductivity, both electronic and ionic, into the cathode side, when you are going to a really thick cathode.
Of course. Thank you very much.
Okay, thank you.
I think we can take one more question from the public. Someone has one? You can.
Yes, I was wondering concerning the temperature. Especially the first two projects, I think, were showing results at 60 degrees. Do we think these technologies with lithium metal can one day work at room temperature? Or is it just 60 degrees is what it's going to be with this type of electrolyte or the lithium metal that limits this temperature?
For Astrabat, I think it could be possible to improve for the temperatures. We can decrease slightly. At the moment, is mainly because the conductivity is correct. The unique conductivity is correct. So we need to decrease the thickness of electrolyte and after improve the contact between the active material and the electrolyte. But effectively, it takes some time to improve all these different systems. But there are no limits technically. After, effectively, if we would like to go beyond 10, or perhaps it will be more difficult to go down.
Yeah, at least for Solidify, most of our tests are typically done at room temperature, and performance is, in terms of energy density, that can be achievable, but then when it comes to charging, then we tend to have challenges there. So then at 40 degrees, we really want to ensure we can boost charging as well as the energy density target. So it might be that within different cells, we show different KPIs, for example. So it's possible, but yeah, challenges really remain, absolutely, especially for charging.
Yes. Just to add something to what they have said, actually, I will say that your question was if we think that it's ascribed to the technology of lithium metal. I will say that it's not a requirement, actually. We can decrease the temperature, but this is more related to the conductivity from one side, but also we need to consider also the resistance. So we may have really good ionic conductivity, but we really need to engineer and work on the interfacial resistance between electrolyte and both electrodes. Of course, the case of the lithium metal is a must to be optimized.
But what I meant is lithium metal coating is easier, plating is easier at high temperature, not forming dendrites or whatever we call them, just it's more homogeneous at high temperature. So is it limiting? Do you think it's limiting or not?
Temperature? Of course, it will be easier if you want to go to, for example, for higher currents, or of course to provide a more homogeneous interface. But I think that will be feasible to go to room temperature with lithium metal and solid state. But of course, so we were discussing before, so it was a 4-year project for going from very fundamental material design to reaching prototypes. So I think that we are paving the way to go there. And there is a lot that we have learned. And I think that if we will have a chance to continue this project, I think that there are many things that we will have in mind when we are designing these new technologies. Thank you. Yep. Okay, in any case, we will have in half an hour the lunch break, so feel free to continue the discussion. Thanks a lot to all the speakers. So she needs to say. Okay, so we will move into the next talk of the day. So I'm glad to introduce Kristina Edstroem. She will be providing the second keynote talk of the day. So just to briefly introduce Kristina, and if I'm pretty sure that all of you know her already. So Kristina Edstroem is a professor of inorganic chemistry at Uppsala University. She leads the Edstroem Advanced Battery Center with 80 co-workers. She is a member of the Royal Academy of Engineering Sciences, honorary doctor at the NTNU. She received the KTH Grant Prize and coordinating the large-scale European Battery Research Initiative, Battery 2030, inventing the batteries for the future. And she is a trustee of the Honor of Faraday Initiative in UK. So please, Kristina, the floor is yours.
Thank you so very, very much. I really had hoped I would be with you in Grenoble, but I am still in Sweden. But it's really interesting to listen to you. These 4 projects, I think you have attacked a lot of the very difficult roadblocks that you have sorry, I should try to find the right presentation here. You get my email address. That was not really what I meant. Sorry about that. Yes, I think it's also interesting to listen how you work with this kind of clustering, because the kind of clustering that is typical what the Battery 2030 Plus initiative has to do. And I'm actually going to ask all of you, and maybe Korsin, you can be the ambassador for Battery 2030 Plus there in the room in Grenoble, because all of what you have learned, what we see now, new projects are coming in at the EU level addressing solid-state batteries. How would they animate them to not go into the same traps that you have done, so that we are just repeating the same mistakes again and again, that we move forward? I mean, you have your own ideas how you want to move forward, but is there something you can actually guide and animate the whole landscape with? I think that's important. So we have this big initiative, Battery 2030 Plus, at the heart of the green and connected society. I think the formal title is exactly like in my presentation of me. That is the future battery technologies that we are addressing. And we are actually celebrating 5 years of existence this year. And so we go through a number of stages where we have a coordination support action, trying to cluster a number of projects from their start. Before hardly they know that they are actually in Battery 2030 Plus. We try to grab them and have a dialogue on different things. And it's a quite large challenge to have a lot of projects, and it's a growing portfolio according to the calls that European Commission has agreed upon that you now know. We had 6 new projects coming out now that applied in September last year, and they start here now. Some started with a kickoff this week and in May. And we have a new set of 8 projects that will start sometime now in October, November. There are more in the pipeline that you will be able to apply. So maybe sometime in 2024, you belong to Battery 2030 Plus and you are part of our family. And maybe a lot of you already are. So forgive me for maybe repeating things you know. But our goal is that we want to accelerate the research, and therefore that we animate the landscape with the findings and try to not just make repetitive things within different EU projects, but exactly learn like you are doing in this meeting, where you ask each other these questions. That is something that sort of is the motivation for us. And we want to provide breakthrough technologies to European batteries, of course, but it's also a lot about long-term European leadership. If you ask DGRTD, which is now our main sort of responsible body at the Commission, we have moved from DG Connect, they would probably say, you are to be disruptive. So we work mainly on methodologies and tools that we can spread information about. While you are concentrating on exactly the solid-state batteries, we can concentrate on methods and helping you studying interfaces in batteries, which you are doing as well. So we have this roadmap, and this roadmap is reviewed and improved, and it's a rather big and comprehensive one with lots of scientific references. So it's not this light version where you sort of read the sketches of what you think of the future, but we try to really say, this is what we need to do in the short term, and this is what we need to do in midterm to reach our goals then. And this roadmap is actually something we will always have. It's always open. You can always have your opinion upon it. You're welcome to improve it, and you don't have to belong to sort of the funding numbers of people in the initiative. It's broader than that. But then we have these projects, and they are to deliver according to the roadmap. So this is a difference compared to most roadmaps you see. We are implementing the roadmap. And I'm very proud to say, fresh from the press, that yesterday afternoon we launched, together with Batteries Europe and BEPA, the roadmap that Simone started the morning to talk about, where the different working groups between Batteries Europe and BEPA have worked on this more like overview type of roadmap, and we launched our last version together with them. So it's a package, and they belong together, and they are connected, and it's sort of not a mismatch. So this is why we're doing that together. And here you have some references where you can find them. So that's important. So the themes we have in our roadmap is not then that we say this chemistry and this chemistry and this chemistry, but we say we want to have a materials acceleration platform, a lot of modeling tools, going into the digitalization era and really bring out the methodology that can give us a lot of learning, high throughput experiments, going into what you have talked about this morning, the difficulty with the interfaces. Interfaces between particles, between metals and particles and polymers, etc. All of that. We're also talking about smart battery functionalities. So we're talking about sensing functionalities, self-healing functionalities, and we have cross-cutting activities like manufacturability and recyclability. So far, the projects have been centered around the 4 blobs to the left here, but now projects are coming in here, October, November, that actually addresses manufacturability and recyclability. And I don't know these projects yet, but it might be so that some of you are in these projects. And then I would really like to know about it. And some of this can be that you're actually looking at solid-state batteries. We know that in the current projects, we have projects looking at solid-state batteries. We have also recyclability that you will discuss later, extremely interesting. And we hear it's low TRL projects up to TRL 4, which is really looking into how far can we go with direct recycling, for instance. So what do we do in Battery 2030 Plus? Well, we work on collaboration aspects. How could the projects help each other, and with what? And it can be extremely concrete. We had the old projects, the established projects meeting a group of new ones just a week ago, and one project said, we find it so difficult to have this sensor, and we can't really make a leakage-free pouch cell. We're trying the same as you, but we have solved the problem. And then they tell about that. And then one project can move on much faster because you learn something from each other. And that is important. You know also that education and skills are extremely important. And what can we promote jointly? We talk because you generate a lot of data. Everyone generates a lot of data in the battery field. How can we really share the open data in a way that we can reuse them and really, yes, learn more from them by using machine learning, artificial intelligence, a lot of data. And so we talk a lot about how can we share this with the projects, and in what format, and what kind of vocabulary should we have describing the different steps. We call it the battery ontology. We have also, of course, IPR and exploitation is important everywhere. We have our roadmap, we have our workshops, optimization and communication. And we have even a communication group to actively promote the communication between the projects and from the projects to the outside of the projects. This is a little bit a summary of what I said. Here are the sort of theme for the collaboration, but it's also a lot about technical aspects within an NDA contract, so you really can tell these different things. So we have been working for 3 years now with 6 projects. They have all been prolonged. So, which is very good because we have just started with 6 new projects. The 6 projects, the big one, the old one is Big Map with 20 million euros, a lot on the Big Map and the modeling, the high throughput experiments, etc. Then we have 3 censoring projects and 3 self-healing projects. Now in the new phase here, we go into 3 projects that really go into the details of interfaces. This is very fundamental understanding and development of method. The synchrotrons in Europe are very involved here. We have also 3 projects merging self-healing and sensing into their projects, which is very challenging. How could you have a sensor that kicking off a self-healing sort of chemical to really make a difference for the battery? But that's what they're doing. So we cover the whole of Europe quite well, from south to north. When with the new projects, we continue to do that. I just want very shortly to give you some results from the Big Map project, because they are so general and it's so much open repositories for data handling and data sharing. So I really recommend you to look at the Big Map website, and if you have questions, you can contact Thijs Wegge from who is the coordinator in this. But the motto, you can say, is how to reinvent the way we invent the batteries of the future. And the idea is this, that traditionally there's a slow development of processes for batteries. I mean, lithium-ion batteries, we can say 40 years. My grumpy old professor said, well, but 50 years now, Kristina, it's 50 years. Sequential discovery and development processes. And you predict, this can be one flow. You predict materials from modeling, you do the synthesis, you go back and say, oh, the modeling didn't understand that we couldn't really make this material. And you have this sequential doing. And of course, you have from the other side the power losses and the deformation and capacity fading, etc. And so the idea is to transcend this sequential discovery process to a much more looping process. And therefore, it's important to have multi-scale simulations to design batteries. And those of you who are really good at modeling, you know this with the different length scales. You do know that you need different kinds of modeling, software and hardware. And the difficulty is often to bridge between DFT and the next level of molecular dynamics, for instance, and up to finite element analysis. But that is something that Big Map is addressing and trying to work on. And that means also that we can go almost from electrons up to cells to do this. And that is really the ambition of this project, to do that. So there are different ways of doing that. And there are some really nice publications on how you can try to do that as well. And what's coming up now is that we are sort of also interesting for the quantum technology flagship, and at the quantum computing and artificial intelligence to accelerate battery research. And this new quantum battery simulation paradigm for multi-scale battery modeling and algorithms can run on emerging quantum computing devices. That's the plan. And then you can integrate all simulation scales from the electronic to macroscopic scale to design this full battery components. So this is sort of the beyond, this is the next step to really have these slower processes to move into a much faster way. So this is something we also are quite involved with the Big Map project, and I think that's important. But we can't do the modeling without having a lot of data from experimental world, because that is really training the modeling. And therefore, I like to specifically lift the work within Big Map, where I think since you are in Grenoble and you are at CA, I think you really should ask the CA people on the very interesting work that Sandrine Leonard is doing for the whole battery community. Trying to build sort of a battery hub for better and faster access to the synchrotrons, and that is sort of tested between CA and ESRF in Grenoble. But I can see all the other synchrotrons are very interested in this model and starting to discuss this more and more. So we have in Battery 2030 Plus actually become a strategic partner in the strategic vision at the EU level for the synchrotrons of Europe. And I think that's very interesting. And this example is an example of how you can combine X-ray neutrons and learn a lot about heterogeneities in graphite materials. A material we studied and published data on lithium intercalation in batteries already 1980s, 1990s. So it's still new things we can learn by the new techniques we have. And we have a very strong platform. So this is also something that you can reach out to and discuss with the different partners we have in this Big Map project, where we actually cover a lot of different methods. And we are using it to make standards and protocols, and trying to make electronic notebooks to really say, we are using this method with this instrumental parameters, and how can we use that further? And that means that we go into this ontologized Big Map experimental matrix, and that is useful then for the modeling. So we all speak the same language. It's a lot about vocabulary. So, and this is just one way of describing every step from a full cell when you break it down to the synthesis and to the different methods. So you can have coin cells and electrode sheets, etc., from the raw materials, and try to make the chain to have this vocabulary. And you see there are many steps. So it's not so trivial, but it's very important for us to do. And this network, when it's created, is a help to identify measurement methods and protocols. So very, very shortly about the smart battery functionalities. We have the existing old projects to the left on this figure. We have the new ones coming on the right. And we see here that a lot of the characterization that is done in Big Map will be taken up by the projects Healing Bat, Opera, OpenCharge, etc. Some of them, like UltraBat, will even go into free electron laser measurements to really understand what's happening to the electron in these electron transfer reactions, and how can we probe that in a better way than we can do today. But the other ones are going into things that you are discussing. How on earth do we do a really good characterization of the interfaces in the solid state battery? So here it would actually be interesting to have this. How do you animate these projects? Do you want to do it, or in what way should one do it? Should we put up a specific conference, workshop, specifically targeting workshop on interfaces in solid state batteries? That is what we can do for the coordination support action that I'm leading. We can organize these things for you and help this. And you know that this is a self-healing picture, but that has to do with interfaces. There are a lot of different things that one can play with at the interface to improve interfaces. Some of this is working for solid-state batteries, some are not. But it's still a lot of things to think about and play. And that's, I guess, is the beauty of our research field, that there is so much we need to know. I also would like to just stress very quickly that we have to improve. We made a bibliometric report, which was published just a month ago, and we can see we are actually behind China and US. These are publications 2018 to 22. We see that it's a very interesting to look at the network coming from Sweden, seeing also all your projects that are so focused in mid-Europe, and the Northern Europe is hardly part of it, and we seem to be in our own region a lot, except for Norway here. But it looks like in the paper we also show how are we doing sort of quality-wise, and we are starting to lag a little bit behind. The quality of US and China is coming. So it's not only about volumes, it's also about quality. So we have to look out a little bit how we do research to really keep up the quality. Yeah, so that's a general thing. We also have a number of activities that are open for everyone and that you can actually be part of. We have Young Scientist event, and that will be in a year or so, where you can send young future emerging research leaders from postdoc up to 7 years after your PhD. It has been very successful. They have made a manifesto that you see in the hands of Stan Whittingham, our Nobel Prize laureate, here handed over from 2 of the Polish young scientists that were part of this network. And this has been a very nice way of having young scientists all over Europe still networking, even if it's now 1.5 years since they met. We also involved in the Battery Innovation Days. I encourage you all to go to Bordeaux in November. We also will deliver a Battery Young Researcher Award. And so look out for that next year, that you actually can support your own brilliant PhDs when they get their thesis, that they can actually be rewarded by Europe. We have an annual conference that you also are welcome to. We have excellent seminars. And here are just some faces where we try to cover the different things. It's modeling, it's experiments, it's high throughput characterization, etc., etc. It's mainly Europeans, but it's also some international stars here involved. And we hope these seminars that are recorded and text can also be used for educational purposes. I do see that some universities use them as seminar series for their PhD students, that they have to look at them and give a little note on what they heard. And I think, and we have used some on our master programs, like Margaret Wolfram-Ferens here, for instance, who talked about how to make electrode. And we have online workshops that are educational. We have had one on self-healing. We have had one really good one on pilot lines made by Sidetech. I know you are in the room, with Lee Planet, for instance. That you find all these on our webpage. And right now we have a course on innovation and entrepreneurship, which is a 2-credit course. It's good for postdocs, PhD students, but also, of course, also younger people, and it's open for everyone. And we have this course is very much online, but it's also will be a physical boot camp in Bordeaux in connection to the Battery Innovation Days. The members of the CSA, the coordination, who try to get these old projects to talk to each other and different aspects, because some are experts on education, some are experts on IPR, etc., and some on the technical contents, because that technical content is very much important in our roadmap. We are well spread over Europe, as you can see. And we have some supporting organization as well. So you can influence new R&I action, new air codes. You can do that from BEPA and Batteries Europe. You can also do that for us and the roadmap. So we are very much working together, these three entities together with some of the IPS days as well. So we have a very good overhearing. We have regular meetings every month to sort of clear things up and not overlap, and so that we can make a good comprehensive sort of information to the European landscape. And what we want in Battery 2030 is be creative. Take action, be part of this. And if you want to really learn more about the big map, the interfaces, the ontologies, etc., we have a whole special issue in advanced energy materials. You can also follow us on X, I guess I should say now, instead of Twitter. So thank you so much. I hope I didn't get too much overtime because you have the lunch coming up. But thank you.
Thanks a lot, Kristina. Okay, so thanks a lot, Kristina, for the nice talk. Now I will ask the audience if there is any comment or question, taking advantage that she is connected online. Okay, so
If you have questions, you have Simon there. He's the deputy, Simon Perrault. You have also Corsin, who's a great ambassador, Corsin from NEMPA. So I think we have many Battery 2030 plus friends in the room. So ask them if there is something special. So thank you so much.
Thanks a lot, Kristina. Thanks a lot. So I think that we can close the session of the morning, and we will have lunch, I guess, that is in the same place as we were having the coffee break. So see you at 1. Sorry.
Maria, just maybe for audience who is connected, they don't have very clear the program. Can you
Sure.
introduce afternoon program?
Yes.
Because there was some update and maybe not all have this information.
Share. This one. The screen. Okay, so I guess that the people connected online can see the screen. So just to remind to everyone, that's true, Andrew, you were correct that we have made some small change. So we will have now a break of 1 hour and a half. So for lunch and networking, we will come back at 1:30, and then we will go directly to the cluster topical sessions. So as we should have explained, I think this morning at the very beginning, for those of you that didn't have the chance to go through the agenda, so there are 3 topical sessions. The first one is related to solid-state battery design and upscaling challenges. Then there is a second session that is related to modeling. So this will be held this afternoon, and tomorrow we will have the third topical session related to sustainability and recycling. So for the people that is online, just remember to connect back at 1:30, and then we will start after the lunch break with the first topical session, okay? So thanks a lot to everyone.